Welcome back to the lectures on quantum chemistry and molecular spectroscopy at the introductory level. Let me now continue with one important result in quantum chemistry and in all of quantum phenomena, namely the Heisenberg uncertainty relation, but with a specific example of how we understand this from the harmonic oscillator model in this lecture. There are other examples that I have already discussed with the particle in a box and in the assignment problems before. I have also mentioned how to calculate the uncertainty through a molecular formula, through a formula. Okay. So, let me start with the basic statements, namely the uncertainty in the position of a particle at a given time and its momentum at the same time at a given t. The uncertainties are related by this inequality h by 4 pi delta x, which is the uncertainty in the position of the particle, and the delta p, which is the uncertainty in the momentum, is greater than or equal to h by 4 pi, and h is Planck's constant. It is one of the cornerstones of quantum mechanics, and if you recall from the earlier statements in this course, delta x was written as the average of the squares of the position measurement minus the square of the average of the position measurement. So, the average of the squares minus the square of the average, the difference between the two is the square of the uncertainty, therefore, the square root of the same is given as the uncertainty. And likewise, delta p was written as square root of p squared minus p whole square. Okay, so, this is one type uncertainty. What is another type of uncertainty relation in spectroscopy? When one studies molecular systems at excited states, the molecular excited states do not have a infinite lifetime, they have a finite lifetime, and the excited state energies are also not very precise. There is a very small spread in the energies of the particles in the excited states, and therefore, one relates to an uncertainty there with the spread in the energy of the excited state, the uncertainty delta E in the energy measurement of the excited state times the lifetime of the excited state, the uncertainty in the measurement of the lifetime. If the lifetime is, say, for example, 5 picoseconds, what is the uncertainty in that 5 picoseconds plus or minus 0.05, 0.01, that delta t. And if the energy of the excited state is something like, say, 5 electron volts, is it exactly 5 electron volts, or is it 5 electron volts plus or minus some small amount? That plus or minus small amount is what is called the uncertainty in the delta E, and this product is also greater than or equal to h by 4 pi. Now, this is for the spectroscopy, and in scattering, chemical reactions, and in general in angular momentum, we also have the uncertainty of the x component of the angular momentum delta j x and the y component of the angular momentum delta j y being greater than or equal to the absolute value of the commutator. There is a formal relation, but for our discussion it is h by 4 pi, the absolute value of j z, the expectation value, or the other way around, sorry. The absolute value of the expectation value, j z. Okay. So, this is another uncertainty relation. For a particle on a ring, you remember that the position of the ring is given by a phi coordinate with reference to an axis, So, the phi equal to 0 or pi by 2, 2 pi, I mean pi, 3 pi by 2, 2 pi, and then the particle on a ring has this circular boundary conditions that anything greater than 2 pi is in terms of the same position below 2 pi. You remember the psi of phi for a particle in a ring should satisfy the cyclic boundary condition phi plus or minus 2 n pi. So, here this is the coordinate and the angular momentum there, which is denoted in the z component, is minus I h bar dou by dou phi. And so, there is an uncertainty there with the coordinate uncertainty delta phi and the uncertainty in the angular momentum delta j, which are complementary variables. J and phi are related to each other the same way p is related to the position minus dou by dou x. So, you have this is another uncertainty relation h by 4 pi and so on. Now, the first of two parts to this lecture is why this formula. X square minus x square square root as delta x, the expectation value. Okay. Let us go back to our elementary statistics. Let us make n number of measurements of some quantity, say, and we get different values. X. Something that we measure, say the temperature of a certain system, and we take identical systems and we measure the temperature, we do not necessarily get the same value. That is a slight variation. Okay. Therefore, we make finite number of measurements and then we take the average. What is the average? The average x bar is x1 plus x2 plus xn by n, which we can write in the summation notation I is equal to 1 to n xi divided by n. Okay. That is the average. Now, the averages do not tell you how far the different values are different from the average. Obviously, if all the values are identical, then the average is also one of them, there is no question. And second, if we did this experiment sufficiently large a number of times, infinitely many times, that is a theoretical limit, then the average that we get is a true experimental average. But in the absence of doing an infinite number of measurements, we do a finite number and we compute the average from the experimental measures. Therefore, the definition of the average deprives the system of the n independent measurements by 1. Why? For the following reason. If you take the errors delta x1, the error is x bar minus x1. If you take the error delta x2 of the second measurement, it is x bar minus x2. And likewise, if you calculate delta xn, it is x bar minus xn. Now, what is the sum of all of these errors? Delta xi. If you look at that, then the errors are not independent of each other, because the sum of all these errors, by the way, the first result is it will become 0. Let us see that now, x bar xi. Okay. If we have to evaluate that, sum over I is equal to 1 to n, x bar minus xi is sum over I is equal to 1 to n x bar minus sum over I is equal to 1 to n xi. Remember, x bar does not change, therefore, this is n times the x bar, and this is already n times x bar. That is how we got the x bar. Therefore, errors are all not independent. Most important, they are not independent in this scheme of things. And second, the errors may be very large. One error may be so much on one side of the measurement, and the other error may be so much on the other side of the measurement, that the errors will cancel with respect to each other. That does not tell how accurate our experiment is. Therefore, we have a second parameter we call as variance, okay. And the variance is the sum of the squares of all the errors xi minus x bar squares. So, the moment you take the squares of the errors, the sums cannot cancel each other. There is no positive error, there is no negative error, there is only one positive error, whether it is on this side or that side, the square of it is positive. Therefore, that tells you how far your measurement spreads out from what is called the median or the average. So, we introduce a variance as something that is divided by n minus 1. Why n minus 1? Precisely because of the fact that your average deprives the system of that 1 degree of freedom, that of the n minus 1 of the n errors that you notice, only n minus 1 are independent, because the last error cancels the sum of all the others, as you have here. Okay. Therefore, there is n minus 1, and the standard deviation is the variance square root, sorry. Square root of variance, and so you write the formula that it is the square root of sum over I is equal to 1 to n x I minus x bar square divided by n minus 1. In the limit of doing this experiment many times, as n increases to a very large value, you can see that we are approaching the true average, and if we assume that we finally get the true average, then all the errors are independent of each other, and therefore, the degree of freedom of that system is that very large value of n, which is technically n going to infinity. The errors become independent of each other, and as n goes to infinity or n is very large, you can always replace n minus 1 by n, and therefore, the exact formula for the standard deviation is the square root of the variance, and that is square root of sum over I x I minus x bar whole square divided by n. And n is extremely large, tending to infinity. Okay. Now, this formula is the one that gives you that uncertainty that you were using in the previous lectures. How? Let us see that. Let us expand x I minus x bar whole square. We get x I square minus 2 x bar x I plus x bar square. So, if you put the sum over I is equal to 1 to n, 1 to capital N, and if you do that, I is equal to 1 to capital N, all of these quantities, then what we have is sum over I is equal to 1 to n x I square minus 2 x bar times sum over I is equal to 1 to n x I, because the average is independent of the individual measurements in this process, and then you have sum over I is equal to 1 to n x bar square. Okay. Now, you can see that this itself gives you n x bar, and this is n times x bar square, because x bar square does not change for any of the terms. Therefore, there are n such terms. So, the sum is simply n times x bar square. So, what you have come up is, if I write it here for this page, you have sum over I is equal to 1 to n x I squared minus 2 times n x bar squared plus n times x bar square 1 times n x bar square. So, the answer is sum over I is equal to 1 to n x I square minus sum over, no, there is no sum, minus n x bar square. Okay. Now, this is just the sum. All of what we have calculated is only that, and that is equal to this number. Therefore, if you have to divide this by n, if you have to divide this by n, you have to divide this also by n. Okay. So, you have sum over xi squared over all the states divided by n. What is that? That is nothing but the average of all the squares, square 1, square 2, square 3, square 4, all the entire experimental n times that you have done. You have summed over every one of those squares and you have divided by the total n. Therefore, this is x square average. What is this one? The n cancels out and this is nothing but the x average square. Okay. The angular bracket is not needed, but the angular bracket is the one that represents the x bar. Okay. So, you see right away that in the limit of infinitely large number of repeatable experiments, identical experiments, giving rise to some random errors, you see that the average becomes the true average and the uncertainty, which is a measure of how far the individual experimental result differs from the true average, and that is given by the standard deviation, and therefore, the standard deviation is what is used as the delta x, as the square root of x square minus x average squared. Okay. The same way for delta p. P square minus p whole square. So, therefore, the origin of the formula is the standard statistics that we all do and the measurement practices that we are familiar with in our schools and colleges. Just same practice that is used to define what is called the deviation from a given measurement in terms of a standardized deviation, and therefore, it is called the standard deviation. Why it is standardized? N is supposed to be infinite. Okay. Therefore, all the errors will become truly a system only, randomized, random errors only. There is no systematic errors. We assume that all these things have been cancelled out. Okay. This is the true formula. Therefore, now we have to show that this delta x delta p is greater than or equal to h by 4 pi for a harmonic oscillator system that we have studied so far. So, that is the second part of this lecture. Now, so let us write down the harmonic oscillator ground state wave function. Remember, n is 0, the quantum number is 0 for the ground state, and that is given as e to the minus. So, let me write the normalization constant first. It is alpha by pi, if that is a notation I had used, 1 by 4 e to the minus alpha x square by 2, where alpha is the parameter for the harmonic oscillator in terms of km by h bar square, and you recall that the Hamiltonian is minus h bar square by 2 m d square by dx square, which is the kinetic energy, plus half k x square, which is the potential energy, and this is the spring constant or the force constant. So, the k and m are the two parameters for this harmonic oscillator. Therefore, our alpha is defined using those two parameters and the fundamental constant h bar square. This is, you can recall, this is what we did in the harmonic oscillator model. And now, with this as the quantity, let me use black, maybe it is brighter on the screen. Let us do the average value x for the harmonic oscillator. The average value x is, you know, it is psi naught x, these are real, therefore, I do not need to use complex conjugate, x times psi naught x dx, and you know that the harmonic oscillator position coordinate goes all the way from minus infinity to plus infinity. So, this is the average value. This function is normalized, therefore, we do not need the denominator. Okay. That is 1. So, this is the average value, and that you can calculate as alpha by pi to the 1 by 2, because there are two functions psi naught square, and you have x e to the minus alpha x square between minus infinity to plus infinity dx. you should know immediately that this is an odd function. Okay. Therefore, this integral between symmetric limits, that is minus a to plus a, minus infinity to plus infinity, is 0. Okay. Simple. Odd integrand f of x is, what is an odd function? F of x is minus f of minus x. Therefore, this integral goes to 0. Therefore, the average value for the position is right in the middle of the x is equal to 0. You have oscillation for the entire positive plane, positive side of the x axis, and the entire negative side of the x axis, but right at the middle is what you call as the average position for the particle. What about the average square? The square of the average, sorry. The square of the average therefore is 0. Okay. What about the average of the square, and that is alpha by pi to 1 by 2 integral from minus infinity to plus infinity e to the minus alpha x square dx. Okay. Because x square simply multiplies the operator x square. This is an operator, essentially these are all operators because they are all position operator, the square of the position operator, the momentum operator, and so on. The square of the operator, therefore it gives you, it only multiplies. So, this is the integral. This is an even function. Therefore, this integral needs to be evaluated. And you must remember that when we wrote alpha by pi 1 by 4 e to the minus alpha x square by 2 as the normalized wave function, what we had used was the fact that minus infinity to plus infinity e to the minus alpha x square dx is pi by alpha square root. And so, we have taken the square root of that and divided the function, and we use that. So, this is known. Let us do the square average, and that is alpha by pi 1 by 2 integral minus infinity to plus infinity e to the minus alpha x square dx. And this is, you can, this integral can be evaluated using partial integration using UV formula. And so, let me write this as alpha by pi 1 by 2 integral from minus infinity to plus infinity x times d of e to the minus alpha x square by minus 2 alpha. So, one of the x is used to write this as a derivative of e to the minus alpha x square, because this will give you minus 2 alpha x times exponential by minus 2 alpha. So, it gives you the x. So, this is what it is, and this integral is, since it is a u dv type integral between limits, this is what? It is u v between the limits minus v du between the limits. Okay. So, if you have to write that, it is alpha by pi 1 by 2, you have x e to the minus alpha x square by minus 2 alpha between the limits minus infinity to plus infinity plus 1 by 2 alpha integral e to the minus alpha x square dx, which is that. D of x is of course simply dx, this is 1, dx is, so it is 1 times dx. So, that is what this is, and this is 0 because the exponential goes to 0 because it is x square. So, the sign of x is irrelevant, minus infinity or plus infinity, that Gaussian function goes to 0. Therefore, no matter how fast the x increases or decreases, this is 0. What is left over here? This is square root of pi by alpha times 1 by 2 alpha. So, that square root of pi by 2 alpha and this alpha by 2 pi both cancel each other, and so what is left over is only 1 by 2 alpha. So, the average value x square is 1 by 2 alpha. The average value x whole squared is 0. Okay. Now, it is easy to show that the average value of p, which is the expectation value of the derivative operator minus I h bar d by dx given by alpha by pi to 1/2 between minus infinity to plus infinity e to the minus alpha x square by 2, the derivative minus I h bar d by dx e to the minus alpha x square by 2 dx. And there is no problem, the derivative of an even function gives you an odd function, and this will give you x times e to the minus alpha x square by 2. And so, this whole integrand will become odd. Therefore, this is 0. Okay. Therefore, the average value of the momentum squared is 0. The average of the square of the momentum is not 0. It is given by minus h bar square d square by dx square, which is the operator for the square of the momentum. It is the average of that, and that if you write down, it becomes alpha by pi to 1 by 2 between the limits minus infinity to plus infinity. You have e to the minus alpha x square by 2, and you have the operator minus h bar square d square by dx square e to the minus alpha x square by 2 dx. Okay. This is easy to evaluate. I leave it to you to take the derivative of this and show that this answer is the following. It is h bar square alpha by 2. That is a simple integral to do. Take the derivative and you will see that it is an exponential, and I will leave it to you to do that. Okay. Therefore, x squared minus x whole squared, the average, the square root, times p squared average minus p average square becomes 1 by 2 alpha, because this is 0, and you have h bar squared by 2 times alpha the square root. Okay. And that is nothing but square root of h bar square by 4. So, it gives you h bar by 2. Therefore, delta x delta p is equal to h bar by 2, and the psi naught x, the ground state of the harmonic oscillator, is called the minimum uncertainty state. If you have to calculate, so you have calculated it for psi naught, you have calculated it for psi naught. If you calculate delta x for any other harmonic oscillator state psi n, this uncertainty for any state psi n, it will be always greater than h bar by 2, and therefore, the uncertainty principle is obviously obeyed by all the solutions that we have arrived at for the harmonic oscillator, and all the expectation values that we calculate for the harmonic oscillator, they have the same property that we expect them, and they obey this uncertainty relations. So, likewise, it is possible for us to show uncertainty relations with the not the eigenfunctions. Please note that the harmonic oscillator function, the exponential minus alpha x square by 2, is neither the eigenfunction of the position operator nor the eigenfunction of the momentum operator, but it is the eigenfunction of the kinetic energy plus the potential energy. So, it is always good to have what are called states which are general, which are not eigenfunctions of either the x or p or the energy or the t time or the jx and jy, that is the angular momentum x component and angular momentum y component. It is important to use a general state to show that the eigenfunctions, that the harmonic oscillator, the way it satisfies the uncertainty, every one of those states would have a minimum uncertainty such as the h bar by 2 or greater than the h bar by 2. Therefore, uncertainty principle runs at the core of all of the electronic structure, quantum chemistry, quantum mechanics. So, it is important to see the value in terms of a simple calculation. Thank you very much.